Hello and welcome. Today we're going to talk about eigenfunctions of the Cauchy-Euler equation. So one might ask, why are we doing this? And the answer, of course, is we want to solve Laplace's equation on a disk. Okay, and this involves polar coordinates. And on polar coordinates, it just turns out that basically when using separation of variables, the eigenfunction problem that emerges from this involves the Cauchy-Euler equation. Okay, so this eigenfunction problem, when I lecture over these things, I like to really look at the eigenfunction problem on its own. I don't like to show a new eigenfunction problem within a separations of variables problem. I find that to be too distracting. There's too much going on. I like to really just focus on figuring out what the eigenfunction problem is on its own. This way we can have this fact, use this fact, the solutions we find here. All right, so that's the only goal of this. So it's going to be a fairly short video. What we really want to do is just show what the solution is to these eigenfunction problems and then move on. So it'll be a nice short video. Okay, so let's talk about the eigenfunction problem. It's going to be r squared p double prime plus r times p prime is equal to lambda p. Okay, so here this is a linear operator. This is a linear differential operator, but it has non-constant coefficients. Again, what we're saying here is that p is actually a function of r, right? So, okay, we're not using x as our variable, we're using r, okay? And here we have these coefficients, r squared and r, which are non-constant, okay? Now, to solve this, we're not going to have any boundary conditions in this particular problem. We're not going to be using those to constrain the solution. So, in fact, there's going to be quite a few of these solutions. We have to organize them. So, again, this is why we're having this video. It's just to detail all of this now so we don't have to fuss over it later. We're not going to be deriving the solution, but rather just reporting what these solutions are. We're going to check them to make sure they're accurate. But again, we have a very simple goal with this video. Okay, the first one we're going to look at is the lambda equals 0 case. Let's see if we can find out solutions for this. And it turns out there are two solutions. Okay, so the two solutions are, I'll call it P0A of R, and it's just going to be equal to 1. So it's just going to be a constant. Okay, and like always with any eigenfunction or any scalar multiple, okay, so let's just go ahead and check this really quick. R squared times 1 double prime plus R times 1 single prime is equal to 0 plus 0 is equal to 0 times 1, which is equal to 0. So that checks out. All right, so we've got our first solution here. Now let's go and check out another one. So there's one more. We'll call it P0B of R, and it's equal to the natural log of R. All right, so this one's more interesting. Let's go check it. So we're going to have R squared times natural log of R double prime plus R squared times natural log of R single prime and that's going to be r squared times, and then now natural log, the derivative is 1 over r, and the derivative of 1 over r is negative 1 over r squared, plus r, oops, looks like I made a mistake on my, there we go. I forgot I put that r to the first power there on my other line. Now it's going to be 1 over r here for my natural log derivative, and we're going to find out we get r squared minus over r squared plus r over r, and that's going to be negative 1 plus 1 is equal to 0. Okay, so that checks out too. All right, so we can box those up, and these are both associated with the lambda equals 0. So we'll call that lambda 0 equals 0 eigenvector. So we're going to find out that for all of the eigenvalues, we're going to find more than one answer. And so again, that's why I think we wanted to study this eigenfunction problem on its own, because it has some quirks to it. It's best just to focus on it and burn it into our brains now so that we don't have to worry about it later. Okay, so with that said, now let's go on to the other cases. So now let's go on to lambda not equal to 0 cases. So it turns out there's actually many, many solutions. There's infinitely many more. So what they are is Pn of r is equal to r to the n. And that's going to be true for n is equal to plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and on up forever. Okay? All right, so again, we have lots of different n values to check. Let's go ahead and figure this out. So let's find out what our lambda n is by just plugging it in. So we have r squared times r to the n double prime plus r single times r to the n single prime. And now we want to know what's this equal to. Okay, so we have r squared n times n minus 1 times r to the n minus 2 plus r times n times r to the n minus 1. Okay, so what's this equal to? Let's sort it out. You notice here that we're missing 2 in our exponent here, but we're able to complete it with the other one. So we have an n times n minus 1 times r to the n power again, plus n, and we have the same phenomenon here where we're down a power, but we're able to supplement that with the coefficient r to the n there. All right, so now we can factor out the r to the n and see what's remaining, and that will be our eigenvalue. So it's n squared minus n plus n. We get some cancellation there. And now we have n squared r to the n power. So that means, of course, that, well, what we started with here was this differential equation. We'll call it L of r to the n. That's the differential equation operator. And we got that out, so that means my lambda n is equal to n squared. Okay, and so this again works for n is equal to plus n minus 1, and plus n minus 2, and plus n minus 3, and plus n minus 4, and on that forever. And note that for 1 and negative 1, the eigenvalue for both of those for positive 1 and negative 1 are both the same, right? It's just going to be that n value, that's value squared. So all the negative n values, they have a positive eigenvalue coming out of it because you're squaring those negative numbers. Same thing with 2. So if I have 2 and then negative 2, that means I'm going to have a lambda negative 2 is equal to negative 2 quantity squared, which is equal to positive 4. Likewise, lambda of 2 is going to be equal to 4 as well. All right, so for each n, excuse me, for each n, there's a positive and a negative. I should say for each n squared, there's a positive and negative n value associated with the n squared eigenvalue. Okay, so that's all the video I wanted to make today. It was just a simple video to show you these solutions. Let's just sum them up right here. We have lambda equals 0. We have 1 and natural log of r. And then we have lambda is equal, so that's lambda 0, and then lambda equal to n squared. We can put this in a table. And then we have, for the lambda equals n squared, we have the r to the n, and then we have r to the negative n there. And this is for n positive. So that's another way to express this now, okay? And as always, any scalar multiple is also a eigenfunction, with one exception though. Of course you can't have the scalar cannot equal 0. So there's our solutions written in a table like that. I hope this video was, again, not really an insightful video, more of just a statement of fact that we can use in future videos. So thank you very much.